Hi, welcome back to our second part in the series of chemical equilibrium. In this particular video, we're going to look at how we can answer some questions in the NSC exams and how we can apply the theory that we've covered in part one of this series. Without further ado, let's continue with our video. Okay, question one comes from the February-March 2015 paper, and this is a question that covers a few theory questions, and it also looks at the reaction rate versus time graph. Let's read this question and see if we can answer it. Pure hydrogen iodide sealed in a 2 cubic decimeter container at 721 Kelvin decomposes according to the following balanced equation. Now, the 2 cubic decimeter, which is the volume, I've highlighted that because we're going to use it later in the question. And then the temperature is at 721 Kelvin. So keep track of those two pieces of information. Anyway, the question continues, but before we continue with the second part of the question, we're going to look at the equation. In this case, we can see that the hydrogen iodide, there's 2 moles of that, it decomposes and it produces hydrogen gas and iodine gas. Now take note that the hydrogen gas and iodine gas are in a 1:1 mole ratio. The delta H, or the enthalpy for this reaction, is 26 kilojoules per mole, which tells us that the forward reaction for this particular chemical reaction is an endothermic reaction. Endothermic reaction. Anyway, the second part of this question is the graph shows how the reaction rate changes with time for the reversible reaction. Question 1.1. Write down the meaning of the term reversible reaction. And that is going to be a basic theory question. But before we continue, let me just highlight for you again that the forward reaction is endothermic and the reverse reaction will always be the opposite of the forward reaction. So that will be an exothermic reaction. Anyway, let's continue. So the reversible reaction, a definition for that is the reaction is reversible when the products can be converted back to the reactants, and it must be the original reactants. Question 1.2, how does the concentration of the reactant change when between the 12th and the 17th minute? Write down only increase, decrease, or no change. For this particular question, learners, you need to take note of what they ask. Do not use different words. When you're going to answer, you must use either increases, decreases, or no change. Don't say that the reactant is changing, or it becomes more, or it becomes less. Don't, or it say, for instance, that nothing happens, it stays the same. You must use the phrases that they've given you. And here we can see that they're actually referring to the 12. There's the 12 and there's the 15 minutes. So it's this part of the graph that is flat, that original part there that is flat. So that indicates to us that the reaction is in equilibrium. And you have to know that when it's in equilibrium, the concentrations of the reactants will remain the same. No changes will take place. So here we know that you can use a phrase. Some questions that will say remains the same, but rather stick to the phrases that they give you. Okay, let's continue with 1.3. The rates of both the forward and the reverse reaction suddenly changes at t 15 minutes. It's this part over here. Okay. 1.3.1, give a reason for the sudden change in the reaction rate. And then 1.3.2, fully explain how you arrive at the answer in question 1.3.1. And that's 3 marks. Now, as I said, it is at the 15th minute in the graph. You can see there's a sharp change, and that will be the forward reaction. And there's a slight drop in the reverse reaction. So when we see that both of these are dropping or increasing, but they're not changing with the same quantity, we know it's temperature. If both of them are going to change with the same length, then I know it will be catalyst Remember, if both lines will be the same length, then it would be a catalyst. Okay, so here we know, as we said, the change was due to temperature. Now, because the rate here is lower than the rate there, it is temperature decreases, or you could say it indicates a decrease in temperature. 1.3.2, how do we explain this? Okay, let's go. Our first point is the temperature decreases both the rate of the forward and the reverse reaction, not just the forward, mention both. And the second point is you need to take note and remember in the beginning of the question, they've indicated to us which is the endothermic and which one is the exothermic. So in this case, the exothermic reaction will be favored. Remember, a change in temperature in such a way that it decreases will always influence the exothermic reaction or always favor the exothermic reaction. And then last point, in this case, the exothermic reaction was the reverse reaction. So indicate that the reverse reaction increases or the reverse reaction is favored. So those are the 3 points that you have to raise in order to gain the 3 marks for this question. Okay, let's continue with the next part. Now, this question is 1.4, and here we're going to do a bit of a calculation. The equilibrium constant Kc for the forward reaction is 0,02 at 721 Kelvin. Now, the equation I've put in here so that we can just refer back to it. And they say 1.4, at equilibrium, it is found that 0,04 mole hydrogen iodide is present in the container. And I want you to calculate the concentration of the hydrogen gas at equilibrium. And that's for 6 marks. If we look at our calculation, we must take note that the number of moles of hydrogen that's going to be produced and the number of moles of iodine gas will be the same. And because the volume for both are the same, the concentration at equilibrium will be the same for the hydrogen and for the iodine. Now, in this case, we can just indicate that the concentration will be represented by X. And if we come up with an equation for the equilibrium constant, it will be as follows. By continuing, we can substitute the values for the constant equilibrium constant, which is 0,02, and then the substitution for the concentration of hydrogen and for the concentration of iodine gas will be X times X. And then the concentration for hydrogen iodide will be 0,04 divided by 2, because remember in the beginning they gave us the volume, which was 2 cubic decimeters. A simple calculation will reveal that the value for X, which also indicates the concentration of hydrogen gas, will be 2,83 times 10 to the power -3 moles per cubic decimeter. Now remember that we used X as a placeholder, or X to indicate the unknown. But remember that X both indicates the concentration for hydrogen gas and for iodine gas. So at the end, you need to identify that the value of X actually is also equal to the concentration of hydrogen gas. You can't just calculate here and then get X as an answer and leave it like that. You need to indicate that hydrogen concentration will be equal to the 2,83 times 10 to the power -3 moles per cubic decimeter. Now, take note, square brackets for hydrogen, not round brackets, and that you're going to put units in here because we're not calculating Kc, we're calculating the concentration of hydrogen gas. Okay, so that's your answer. 1.5, calculate the equilibrium constant for the reverse reaction. Now, this is a question that they've asked a few times. The reverse reaction, very simple, it's the opposite. Or it's the reverse, or it's the inverse that we have calculated before. And in this case, Kc for the reverse reaction will be your previous answer, but you're going to get the inverse, so that will be 1 divided by 0,02, and that gives me 50 as an answer. Now remember that 0,02 was part of our calculation, but it's not what we calculated, it's what was given to us in the beginning of the question. So we're going to take that value. 1,6, let's look at this particular question. The temperature is now increased to 800 Kelvin. Remember, the temperature was 721 Kelvin. It is now increased. Temperature is the only factor that affects the equilibrium constant. So an increase in temperature is going to affect the equilibrium constant, but it doesn't mean it's going to increase the equilibrium constant. It depends which reaction is the endothermic reaction, because the endothermic is the one that is favored when the temperatures increase. So it's important that you go back to your equation and the information that you wrote down. How will the value of equilibrium constant for the forward reaction change? Write down increase, decrease, or remain the same. Take note that here your choices are different from the choices in the first case when we had another question. Okay, in this case, remember that we had this equation. The forward reaction was endothermic, so an increase in temperature will favor the endothermic reaction, which means I will produce more of the products and less of the reactants. If I put that in equation, then I will find that the exothermic reaction is not favored in compared to the endothermic. So the endothermic is faster compared to exothermic, and my Kc value is going to increase because the concentration of the products is increased way more than the concentration of the reactants. Okay, so that's the answer for 1.6. Question 2. Initially, excess ammonium hydrogen sulfide, which is a solid, is placed in a 5 cubic decimeter container at 218 degrees Celsius. The container is sealed and the reaction is allowed to reach equilibrium. According to the following balance equation, there we have our equation. We see that delta H is greater than 0, so that means that the forward reaction is an endothermic reaction. State Le Chatelier's principle. We can see here, when the equilibrium is in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will cancel or oppose the disturbance. That definition is exactly the same as in the guidelines. Make sure that you memorize and commit it to memory so that you can reproduce it in the exam at any given time. Question 2.2. What effect will each of the following changes have on the amount of ammonia at equilibrium? Write down only increase, decrease, or remain the same. 2.2.1. More ammonium hydrogen sulfide is added, and here the answer is remain the same. Why? If we take note that the phase of the substance here is a solid, and solids will not affect the equilibrium at any given time. So it remains the same. 2.2.2, what will happen if the temperature is increased? And here we can see that it will increase. Increases, okay? Let's move to our next question. Question 2.3. The equilibrium constant for this reaction at 218 degrees Celsius is 1,2 times 10 to the power negative 4. Calculate the minimum mass of ammonium hydrogen sulfide that must be sealed in the container to obtain equilibrium. So when they say must be sealed, that is the amount that's going to react. Anyway, when we continue with this question, there are two ways that we can solve. We're going to look at option 1 and then go to option 2. Now take note that they will provide us with information of the ammonia. Okay? That information that we're going to get, this is our given information, we must use that, and any information that is given to you must be converted to moles. Take that moles, relate that moles to the ammonium hydrogen sulfide, and then once you have that in number of moles and you relate it to that, you can take the moles of ammonium hydrogen sulfide and then convert that to what was asked in the question. And remember, we have to calculate the mass of ammonium hydrogen sulfide. Okay, So there are mainly three parts. We're going to look at the information here, and then the second part is to relate the moles, and then the third part is to calculate what they've asked us. In this case, it's the mass. So let's look at the answer. How do we answer this question? But firstly, let's remember that the volume for this reaction was in 5 cubic decimeters. The first part of the calculation is where Kc equals the concentration of ammonia times the concentration of hydrogen sulfide. Those are the two products. I'm not going to include my reactant because it's a solid. I've been given Kc, and in that case, the concentration of ammonia will be the same as the concentration of hydrogen sulfide, which in this case is 0.011 moles per cubic decimeter. Use that concentration with the volume, and then we can calculate the number of moles of ammonia that actually formed in this reaction, which is 0.06 moles of ammonia. Once I have that moles of ammonia, relate that to the moles of the reactant. And that we can see it's a 1-to-1 mole ratio. Therefore, I will have 0.06 moles of ammonium hydrogen sulfide. And once I have that moles, I can use it to calculate the mass. Now, if you work out the molar mass of my reactant, I will see that is 51 grams per mole, and that 51 times 0.06 will give me an answer of 2.81 grams. Now, depending on the periodic table and the values that you're going to use for molar mass, you should get a value between 2.55 and 2.81. Any value between that, including those two values, will be accepted. So that's the answer if we use option 1. Option 2, we can make use of the table. This is the RICE table, or the ICQ or ICQE table. Different teachers will have different ways of referring to this table. Now, we don't have all the information, so it's not so much important what you write here. It's more important what you write in the columns of the products, because the reactant is a solid. Now, the amount of mole that has changed in this, I know that X mole of the reactant decomposed, and it produced exactly the same mole of products for each product. So it will be XX. And the quantity of the moles of the products at equilibrium will be 0 plus that X will give me X, and it's the same for hydrogen sulfide. The equilibrium concentration in this case will be X divided by 5, because the volume is 5. If we continue here, we'll notice, in the previous question, I told you that the molar mass for ammonium hydrogen sulfide was 51. Here I show you the calculation. If we use that, we may continue with the Kc equation. And this time we're going to substitute X divided by 5, which will be the concentration. It's a different unknown. And then if we calculate X, it is 0.0547 moles. By substituting that into my formula so that I can calculate the mass, will give me 2.79 grams. So it's an answer slightly different from the previous one, but it falls within the range that they've given me, and that's still accepted. So that's the second option. I think those two options are fairly easy to understand, and you should be able to understand and get it to grips and be able to do this in the exam. However, I think option 1 is a much easier option, because I think in general learners tend to do a lot better if there are no fractions involved. So go over it again and try to master it, and then you can reproduce it if a question that is similar to this is asked again. Okay, we continue with question 2.4. The pressure in the container is now increased. Now, when you increase the pressure, they do so by decreasing the volume of the container at constant temperature. Now, they say constant temperature because we know that temperature will also influence the equation. So we don't want temperature to also influence it, while the pressure is an influencing factor. So that's why we say at constant temperature. 2.4. How will this change affect the number of moles of the hydrogen sulfide produced? And fully explain your answer when you give your answer. Okay, so we'll see that before we continue, seeing that we're going to look at pressure, we need to count the total number of moles of the reactants. In this case, there are no gases, so therefore 0 mole. And the total number of moles of your products, and in this case, the products is only one gas, so there's 1 mole. So I can see it's an unequal amount of moles on both sides of the equation, therefore pressure will influence this reaction. And if I'm going to apply pressure, then I know that the equilibrium is going to move, and one of the reactions is going to be favored, and the reaction that's going to be favored will then be the reaction that's going to produce less moles. Okay, and in this case, I can see it's going to move towards the product side if I increase the pressure. Okay, so an answer for this particular question is as follows. Now remember, they wanted to know how will this change affect the number of moles of the H2S. Now take note, it's a product, and we know that the reverse reaction will be favored. So in this case, the concentration of H2S will decrease. And the reason why that will happen is because when the pressure is increased, the reaction that leads to a small amount of gas in the reaction will be favored. So that's 1 point. And then we know that the reverse reaction will lead to the reactants. And in that way, the reverse reaction will be favored over the forward reaction. So there you have your 3 points that will give you an answer. Remember, this question, it will be negative marking will be applied here. So if you make a mistake in the first part of your answer, then the examiner is not going to look at the second part. So think carefully and work it out carefully to decide between whether it's going to increase or decrease. Okay, that is the last of this particular video. I want to say thank you for joining us. I hope that you understand what I've explained. And remember, you have to go over it again so that you can master the concepts and be able to reproduce it. Please continue to follow part 3, and I hope that you will learn and you understand how to answer these questions in your upcoming exams. All of the best. Thank you.